Good evening, everyone. Welcome to NPTEL tutorial session for the course Principles of Organic Synthesis, which is taken by Professor T. Punniyamurthy from Chemistry Department, IIT Guwahati. And I am Sri Lakshmi S., a PhD scholar in IIT Bombay in the Department of Chemistry under Professor Krishna P. Kaliappan. So I have been taking the tutorial session for the principles of organic synthesis for the last 12 weeks. So today is the 13th week and here we will be having a summary tutorial session. So here what we are planning is to uh, discuss some questions basically because in the last tutorial session we didn't discuss any questions regarding the week 12 lectures. We were going through the lecture contents only, so today we will be discussing some questions related to those topics. Before that, maybe we can summarize the whole 12 weeks course, what all things we have learned. We will have a brief discussion about that. So these are the main topics which we have covered, which professor have covered in this course. First was formation of aliphatic carbon-carbon bonds through base catalyzed reactions as well as acid catalyzed reaction. So in those lectures, we came to know about aldol reactions and related reactions, which can be classified, which can be carried out by both base as well as acid media. Then we have seen several organometallic reagents and the formation of aliphatic carbon nitrogen bonds, electrophilic as well as nucleophilic aromatic substitution, then reactions involving aromatic diazonium salt. Then we have seen several molecular rearrangements and several reactions and reagents containing phosphorus, sulfur, silicon, boron, and tin. Then towards the last lectures, we have seen free radical reactions and then yeah, and these are the main references which you can follow for referring to these topics, mainly Caruthers, Glader, and Carey Ansenberg. So in the lecture first week lectures, we have seen several aldol and related reactions like Novinagel, Henry reaction, Perkin reaction, and Claisen condensation, Thorpe reaction. Then we have discussed several problems related to that, and in the yeah, moving to the week 2 lecture, we have seen this base catalyzed carbon-carbon bond formation, Michael addition, Robinson annulation, and such type of reaction. Then in the yeah, in the third week we have seen acid catalyzed carbon-carbon bond formation, where we have seen this Manish reaction, which is an important reaction in organic chemistry. Then Friedel-Crafts reactions involving both alkylation as well as acylation reaction and its mechanism as well. Then Prince reaction. Yeah, these were the main things which we discussed in the week 3 lectures. Then in the week 4 lectures, we have been discussing about organometallic reagents, especially Grignard and organolithium reagents, and what is the difference between 1,2 addition as well as 1,4 addition. And then in the week 5 lecture, again we were discussing about Gilman reagent, that is when we are using copper along with magnesium or lithium, we will be getting 1,4 addition rather than 1,2 addition, that is a conjugate addition will be taking place. And then we have seen some copper mediated reactions like laser coupling, Castro Stephens coupling, then zinc mediated Reformatsky reaction, zinc copper couple mediated Simon Smith reaction, then this palladium or nickel catalyzed zinc and organohalides, Negishi coupling reaction, then oxymercuration, demercuration of alcohols, alkenes, and then Ritter reaction, Gabriel synthesis for synthesizing this thalamide. So these were the main topics which we see in the week 5 lecture contents. And then in the week 6, we have seen this reactions of imines as well as enamines, where we have seen this Eschweiler-Clark reaction, Stoke-enamine synthesis, Robinson-Schoff reaction, Hell-Bollard-Zelinsky reaction, Strucker synthesis of amino acids from aldehydes, Bucherer-Berg's reaction. Yeah, and then in the next week lecture content, mainly We have seen this electrophilic aromatic substitution reactions, its mechanism, which are the key electrophilic aromatic substitution reaction, what is the role of different activating and deactivating groups in such aromatic substitution reaction. Then this substitution reactions involving Gattermann Koch reaction, Hausch reaction, Bilsmeyer Hack reaction, Riemann reaction, Kolb Schmidt reaction, Manish reaction, Duff reaction. And I think the next lecture was about nucleophilic aromatic substitution reaction. No, before that we have seen this nitration sulfonation, which is also electrophilic aromatic substitution reaction. Then we have come across this nucleophilic aromatic substitution reaction. So in the nucleophilic aromatic substitution reaction, we have seen several types of mechanisms, including addition, elimination, eliminate first elimination and then addition type of mechanism, and this benzene involved mechanism as well. Then yeah, then we have seen this rearrangement reactions like Wagner-Mervin rearrangement, which is basically used for the migration of alcohols to give alkenes from this alcohols. And then this Pinacol rearrangement, then there's Reup rearrangement, Curtius rearrangement, and the related reactions involving this nitrine, that is Lawson rearrangement, Schmidt reaction, and Hofmann rearrangement. Then we have seen this Baeyer-Williger oxidation, Dakin oxidation and its mechanism, then this Omelette-Hauser rearrangement, Favorsky rearrangement, Wittig reaction, Mitsunobu reaction. Yeah, then in the last week lectures content, I guess, we have seen this Corey-Chekovsky reaction, which involves epoxidation, acidination, as well as cyclopropanation. Then we have seen this silicon-mediated Peterson olefination for the formation of this alkenes. Then hydroboration, oxidation of alkenes to get alcohols from alkenes. And then the Suzuki coupling, which is a palladium mediated reaction between this halides as well as borane complex. And this Chile coupling, which is palladium mediated but between tin compound and organohalides. Then this Hans-Dicker reaction, which will convert the ester or carboxylic acid into corresponding alkyl halides. Then we have seen this sodium mediated acyloin condensation reaction. Then this Hoffman Loeffler Freytag reaction, Barton reaction, Barton McCombie deoxygenation, as well as Barton McCombie decarboxylation. Yeah, now I think, yeah, so that was about the whole 12 weeks lecture contents we have been discussing so far. So today first we will start with this problem. So predict the major product of the following reaction. So here this compound we are treating with the sulfur halide, so which will be the correct answer out of this four options given here. So as we can see from the options, either it is doing cyclopropanation or it is doing an epoxidation reaction. And if it is cyclopropanation, then it can be either with this double bond or with this double bond. Or if it is epoxidation, it will be including this ketone. So which will be the possibility if, if we are treating this compound with the sulfur halide? So, as we have discussed in the last week, this is the correct answer where this double bond will be getting cyclopropanated using the sulfur halide, and the mechanism goes like this. So, if we have a sulfur halide which is basically like if we have this SMe Me this plus, so a base can attract proton, base can take proton from one of this methyl group generating the sulfur halide, so that will undergo addition, one to addition to this carbonyl compound. So if that is happening, in that case it can undergo this nucleophilic addition and it will result in the formation of this epoxide. But if it is not the case, what will happen is that this here the CH2 minus. So if we have both these options like epoxidation as well as this cyclopropanation will be happening first in the case of sulfur halides rather than cyclopropanation. So in that case, what is happening is that this CH2 minus will attack over this center, and then this will attack over that. I will draw here maybe. Yeah. So the CH2 minus will attack over here, and then this bond can shift over here and this will go over here, resulting in this compound. Here O minus, here Me, here CH2, and then S double bond O, Me, Me plus. Then what will happen? This bond will come over here, like here it will be this double bond will be there when this enolate anion is generated. Then when this, instead of coming back here, this can attack over this center and this will be leaving out. So this dimethyl sulfide will be the one of the byproducts which we are getting, and this will attack over here leading to the cyclopropanation. So why this not here, like here one double bond is there, why this double bond is not getting affected? Because here this is in 1,4 fashion, so this CH2 minus is attacking over this center in a 1,4 fashion. It is a conjugate addition, and because once that conjugate addition is happening, this bond will migrate to here and that will result in the formation of an enolate. But there is no such case with this double bond. So when the enolate will come back, that will be the driving force for the elimination of this dimethyl sulfide also. That's why the addition is happening over this double bond rather than this double bond. I hope it's clear. The mechanism I have given here is for epoxidation, but the similar is the case. First this will be happening, and if enolate is like O minus is going here, and in the case of a 1,4 addition, this type of reaction will be happening, whatever we discussed, rather than this epoxidation, because this is an alpha beta unsaturated carbonyl compound system. Moving to the second question, predict the major product of the following reaction. So this compound upon treatment with this copper iodide, PPH3 and K2CO3, which will be the major product out of this four options. So this we have already discussed several times before also. It's a coupling reaction basically. So first what is happening, this copper will undergo oxidative addition with this, or we can say it will take this proton and it can undergo addition over here. Then this will attack over here and this I minus will be leaving out. So it is basically a simple coupling reaction. Like we have previously discussed the Castro Stephens coupling, Glaser coupling, such type of coupling reaction. So this is also a coupling reaction between this terminal alkynes and vinyl iodide, which is mediated by the copper. So the correct answer is option A. Moving to the third question, predict the major product of the following reaction. This silicon compound and this MeCOCl, when we treat it with this titanium chloride, which will be the product and which reaction it is. So here the correct answer is this option B. And here this is already discussed in the lecture video. So here what is happening is that this AlCl3 or this titanium chloride, which both are Lewis acids, it can react with this one second. Yeah. So it will react with this MeCOCl and AlCl4 minus leave out, which will generate this carbocation. That is MeC double bond O plus. Then what is happening is that this double bond, yeah, it is given here. So this double bond can attack over this carbocation, which will result in the formation of this compound. So that will be giving. So if this is attacking over this center, what will be product will be this here SiMe3, and here we will be having C double bond O CH3, and here we will be having a carbocation, right? So this double bond attacked over this carbonyl carbon with the positive charge, so that will generate a carbocation at this center. So we will be getting the species. Then what is happening is that this carbocation will be stabilized by the elimination of this group as this Me3SiCl, because initially this Cl minus was also here. So that will leave out, which will result in the, I think, yeah. So that will be okay. So this is not attaching here. One second. So we will have the first intermediate as this, and here it will be attacking, so it will be C double bond O CH3, and here the carbocation will be there. So that will be stabilized by the elimination of this group. So this bond will shift to here and this will leave out to form this compound. So double bond will be generated at this position and this carbocation will be stabilized also. So it is a similar reaction. So here what is happening is that this aromatic double bond is attacking over this carbon center to generate this intermediate at first, and then again this SiMa3 is leaving out to give this compound. Moving to the next question, predict the major product of the following reaction sequence. So this sulfur compound upon treatment with this ethyl bromide, sodium hydride in sodium liquid ammonia condition or sodium ammonia condition, which will be the major product. So here the correct answer is this one, option A. And so this is an example for a rearrangement reaction. So here what is happening is that first we will see one example and then we will go to the problem. So here what can happen is that if we have a sulfur halide like this, so if we compare this product and the reactant, we can see here an R dash group, that is from this position it has migrated to this position. So we will be getting this compound as the product. So the positive charge on sulfur is stabilized as well as this negative charge on this carbon is also stabilized. When the substituent is allylic one, then what is happening is that this will like a 3 to sigma tropic rearrangement, we can say this negative charge will attack over here, this bond will come over here, and this will come over to stabilize the positive charge on the sulfur, that is it will give this compound. So here whatever example is given here, that is exactly the same which is shown here. So here what is happening is that in the presence of this ethyl bromide, the sulfur will attack over this ethyl group and thereby creating an S plus charge that will be stabilized this by this bromide ion, so it will be existing as this compound. Then what is happening in the presence of sodium hydride, this proton will be abstracted. So here are two acidic protons. So one of the acidic proton will be abstracted, creating a negative charge over this carbon. So then there is two possibility. Either a 1-2 shift can take place. So 1-2 shift means this ethyl group being here and this group can migrate over this center, that will give this compound. And if a 3-2 shift is happening, then what is 3-2 shift is happening means, so it will be like um, one second. Yeah. So 1 2 shift means this whole group is getting migrated into the sender. Then if it is a 3 2 shift, that means, so as we can see in this product, here is the dimethyl group. So mm, yeah, I think this is getting migrated to here, and then this is breaking, and this is getting transferred into here, so that this dimethyl group will be adjacent, and this will be external double bond will be here like this. So this will be migrated to here, so this will be 3 2 shift. So if 3 2 shift is happening first, and then for this removal of this SET group, we are using this Birch reduction condition. That is a radical pathway using the sodium in liquid ammonia. This will be eliminated, which will give rise to this product. So here the correct answer will be option A. So first ethyl bromide will create this SET, and here plus charge, then NaH will undergo, NaH will take this proton, creating an anion at this position. Then 3 2 shift is happening, for followed by the removal of this SET group to get the product. Moving to the next question, predict the major product of the following reaction. So this, upon treatment with this palladium, not palladium, lead tetraacetate, which will be the major product. So this also we have seen in the lecture video. So I am not going into the details of the mechanism. So here actually we are heating the reaction mixture. So that will result in the elimination of two molecules of nitrogen, and we will be getting a benzene as the product. So this is one of the method to create a benzene. So the correct answer is option A. Moving to the next question. Predict the major product of the following reaction. So this aniline derivative we are treating with this thiol derivative. Uh, so this is thiophene, and we are treating it with the sodium methoxide and then hydrogen nickel condition. So which will be the major product? So here, what is happening is that, so first when this thiophene is treated with this compound, the Cl minus get eliminated and this lone pair of nitrogen will attack over this center, and that will create this positive, or yeah, this will be generated at first. Then this O methoxide from the sodium methoxide which we are using in the reaction mixture, it can abstract a proton from this center. So that will be generating this species. If the proton is generated, it will generate this anion which will attack upon this center, that then this aromatic bond will come over here and this will be eliminated. So this bond is getting formed, we will be getting this species. Then hydrogen in nickel condition, what it will do is it will eliminate this sulfur, and this will be, the center will be getting protonated as well as this center will be getting protonated. So we will be getting this 1 2 3 4 carbon chain ortho to this NH2 group. So here the correct answer will be option B. I hope it's clear. Moving to the next question, predict the major product of the following reaction. So here we have a dialdehyde which we are treating with the titanium chloride zinc in THF. So which possibility will be happening here and which will be the product out of this four options, and which reaction it is basically? So this is a simple aldol reaction, aldol condensation reaction we can say. And this zinc mediated aldol condensation reaction, so this titanium chloride can coordinate with both of this oxygen, which is because it is a Lewis acid. And after generating this anion over this center, that will attack over here, so it will generate a ketone as well as an ketone as well as an alcohol. Yeah, so I think one ketone is missing over here. Yeah, so this will attack over this center, that will generate 1 2 3 4 5, 1 2 3 4 5 6. Then I think it is not aldol, but it is a kind of like radical coupling reaction kind of reaction. So this here, this carbon carbon bond is getting formed. Then only we will be getting a seven membered ring. One, two, three, four, five, six. Yeah, this carbon carbon bond is getting formed, and then this OH as well as this OH is getting eliminated, which will result in the formation of a double bond over the center. Yeah, so this is not aldol, this is basically a coupling reaction. I think this is mediated by radical, and we will be getting this here carbon radical, and this oxygen radical, and that will be eliminated mostly as water molecule, this 2OH, and then this carbon carbon bond will be formed, double bond will be formed. So first this carbon, this radical combination will give the single bond, then again by the elimination of this hydroxide radicals we will be getting the double bond. Moving to the next question, predict the major product of the following reaction. So, this toluene, upon treatment with this fluorobenzene derivative using this copper and DTBP at 110 degrees Celsius, which will be the major product here. So, this DTBP is di-tertiary butyl peroxide. So, what will be the role of that peroxide when we are using it with copper, and which reaction it is? So here the correct answer is this one, option A. So what is happening here is that this is a copper catalyzed oxidative alkylation which help in the formation of this carbon carbon bond. So what is happening is first this DTBP, that is di-tertiary butyl peroxide, which upon treatment with this copper we will be getting this CH3 radical, then this acetone, and this radical will be produced. So this is our reactive intermediate, and once this is formed, that will react with this toluene, which will leave one of the proton as hydrogen radical to give the tertiary butanol, and so this radical will be generated. So we are using this tertiary butyl peroxide radical to generate this radical. Then when we are treating this with this compound, what will happen? This double bond can undergo homolytic cleavage, creating one radical at this center and one radical at this center. Then these two radicals are getting combined, which will result in the formation of this free radical. Then again this bond can undergo homolytic fission, which will eliminate this NO2 radical, and here one radical will be generated that will combine with this radical to form a double bond at this center, and we will be getting this product. So this is a, whenever we are seeing a peroxide mediated reaction, mostly it will be undergoing through this radical pathway. Sorry for the too much noise outside. So I hope this is also clear. So we have only this 10 questions for today. So today's session was just a quick summary session where we have seen what all things, what all topics we have discussed so far in the 12-week tutorial session. And then we have seen this questions which was based on the week 12 lecture content. So I hope this session was helpful for you. So with this, we will be concluding today's lecture session. Thank you for joining. If you have any questions, you can ask. Okay, if there is no more queries, we will wind up today's session. Thank you.